Okay, last class today. We have to do all the rest of statics today. So first, let's be clear on what's left this semester. Any assignments that you haven't finished, that you haven't turned in? All problem sets are due if you're turning in a hard copy. By Friday, I don't even know if school's open until 6 p.m. And if you're turning in an electronic copy, it has to be one PDF per assignment. Turned into the Dropbox on D2L. Sunday at 11:59. 59.0 p.m. Okay? Any questions about the assignments? And then the only thing we have left is Exam 5. That is, unfortunately, Thursday at 8 a.m. in this room. And the topics are friction and everything else. And actually, we didn't do internal loads on the last one either, but you get the idea. So I said friction because you haven't turned in an assignment. Maybe you're like, I was going to say you haven't turned in an assignment with friction, but some of you are like, I haven't turned in any assignments. But there's no assignment with friction on it. You're responsible for those problems yourself. It would be a really bad idea not to go through those problems, even though you're not turning them in. And office hours next week. I'm going to keep the same ones. They'll work pretty well for the final schedule. So that's Monday, 3 to 6 in S1324. Tuesday, 1 to 2 in my office, 2302. And Wednesday, really it's 5 to 6. Let's say 3 to 6 in S1324. So I'll do the 2 extra hours on Wednesday. Usually that's short on Wednesday because I have a lab, but not next week. So you got a lot of chances to talk about this stuff before Exam 5. Just to make things interesting, though, office hours next week, half the stuff I tell you is going to be wrong. Okay? Okay. Just to sweeten the plot thickens.
You want to see if you can correct him?
Yeah.
And tell us the correct answer after.
Okay, I'll tell you the right stuff. Okay. Any questions about anything the rest of the semester? All right. So today we have to finish talking about friction. If we have time at the end of class, I'd be happy to talk about questions on homework or whatever, but let's make sure we get through the material we need to. So all that's left in friction is bearings. And there are two types of bearings. Journal bearings and here's what journal bearings are. You can think of it as like a pin joint is a journal bearing. Something that bears load. The two that we are going to deal with both involve rotations of axles. Okay, so what we have is an axle that's rotating in like a pin joint, you can think of it. And the surfaces of contact on the axle is this all the way around. And on the bearing is this. Okay, that's a journal bearing. And then the second type is a thrust bearing. And in that one, the axle's rotating this way. Well, it can be rotating either way. There has to be some force causing a contact between this and, in this case, say we're talking about like a wall. It's hard not to draw that picture and make it look a little inappropriate, but let's all try to be mature people about this. So let's say we have this force. I was about to name that force P. I'm not going to do that. Again, because I'm so mature. And the surface is in contact. On this axle, well, the surface that's in contact on the axle is obscured, but it's this. And on the contact, it's this. Can everyone picture what these two different types of joints, these two different types of bearings are doing? I want you to notice one thing. pin joints that apply thrust are combined journal and thrust bearings. So like an example would be okay, so there's a little flange on here that keeps this from sliding this way or that way. And if there's a force pushing these two together, I'll draw it here. Then, you know, as long as there's always going to be some kind of friction between surfaces. There's a contact surface between the inside of the pin and the outside surface of the axle. That's the journal bearing. And there's also contact between the wall of the bearing and the obscured side of that flange, and that's the thrust bearing. And then you'd have to deal with both of those two types of friction. Yep.
And when you say the obscured side of the flange, you're talking the inside.
The inside, the part that's touching that bearing. Okay, so let's start with journal bearings. Yes.
So the formula for belt friction and quite possibly the formulas for this, will those be given to us, or are we expected to?
The belt friction formula will be given. The two bearing, the other three things. So square threaded screws and the two types of bearings, you need to be able to derive those formulas.
Got it.
I didn't derive the belt friction one, so I'll just give you that. Okay, so journal bearing, drawing it the other way, just to show off. And let's say it's rotating this way. And let's say that there is a force applied to each end of the axle. And there's a force applied to the bearing that's equal and opposite. So let's call this the weight W, and we'll call this W over 2, W over 2. So, you know, I'm sort of, let's think about it like this. That is, so this is fixed to the ground. That bearing is just attached to the ground. And so there's something applied up above that's weight is distributed on the two ends, and they're being supported by the fact that this bearing can't sink into the ground.
Oh, so it's just a reaction to the floor.
Yeah, right. And we're going to take a view like this. Poor sucker. Okay, so, and we're going to draw a free body diagram from his point of view of the axle. So what he sees is this. He's just looking straight down the axle. There is, if we're doing a free body diagram of that whole axle, we have two of these forces, you know, W over 2 plus W over 2 is equal to W. The axle is rotating this direction. And if there was no friction at all, the reaction force from the ground would be applied straight up through the center. Okay, and that would be that. It would be static equilibrium. It would be, and this spinning would happen freely forever with no additional torque applied. But what happens due to the friction is if you're representing the force applied to the axle by the bearing as a single point force, that point force drifts to the front. And you end up with a W applied offset from the center like that. And because this applied force is offset from the center, some amount rho, that force W produces a moment. So since that W force doesn't have a line of action through the center, it produces a moment. Yeah, well, I didn't really say, but the reason is, so where is this axle in contact with the bearing? Well, it's in contact everywhere, you know, the whole way around. But we're representing that whole distributed load as a point force, which is, you know, we've used that idea before. And if you experimentally measure where that point force is that gives you an equipolant system, what you would see is that as this thing spins, that point force drifts towards the front. You can think of that as like an experimental result. Okay.
Just out of curiosity,
Yep.
if you had a free body diagram like this, and this is just curiosity,
Yeah.
could you have a distributive load around the entire thing with a circular object like this?
Yes. Yes, you could. We just haven't talked about how to do it, but
Anyways.
yep.
just-
Yes. It's not terribly hard to do. You just have to think about distributed load vectors instead of single direction distributed loads, and then you have to deal with the components.
If the axle spun the other way, would the W be on the other side?
Yes. You know, it has to be on the way that that moment slows down the rotation.
Sure.
You know what I mean? So if you could figure out a way to make it spin this way and have the W act over here, you have a perpetual motion machine. That's awesome. Okay? You can take the rest of the day off.
Well, right, really.
Yeah, exactly. That moment is what slows down the rotation. Okay, so let's look at an expanded view so I can, bless you, so I can look at some details of all the angles and distances and stuff. expanded view of the axle. So here's the center. There's the center line. And there's a force W that's applied here. We also have this W applied from the top. And that force W is made up of two parts. Oh, and this distance here is rho. So this W is made up of two pieces. A normal force and a friction force perpendicular to the normal. That's equal to the coefficient of friction times the normal. These are perpendicular. So based on what the coefficient of friction is, we can figure out what this angle is. Okay? It's not clear yet why we want to do that. Could figure out theta from that coefficient of friction.
Can you also figure out theta just by having n?
Well, we don't have a way to calculate n.
Okay.
But yes, you're right. If you measured that, that would be enough too. But mathematically, we can just figure it out from what the coefficient is. Okay, so why would we want to figure out this angle theta? Well, the answer is that angle theta is also equal to this angle theta. And the hypotenuse of this triangle is just the radius of that axle. That's easy to measure. And we want to find theta because that rho that we need to calculate the moment is just equal to r times the sine of theta. You see that? That's just right angle trig. Okay, so let's think about this triangle, come up with an expression for theta from this, plug it into this to get rho, and then we'll calculate that moment. Okay, so first, find theta in terms of the coefficient. So we have a triangle like this. There's our theta. The hypotenuse is W. This is N. This is mu N. And so theta is just equal to the inverse tangent of mu n over n. Those n's cancel, and you just get inverse tangent of mu. And then the second step is now express the moment due to friction in terms of this coefficient of friction. So we have a triangle with an angle that's equal to the inverse tangent of mu. This is rho. The hypotenuse is the radius of the axle. And so theta is just equal to r times the sine of the inverse tangent of mu. And you might remember somewhere in the recesses of your mind that you can simplify stuff like this. So let's set up a right triangle that has. Okay, so if you don't like simplifying stuff, you don't like math, you know, you probably shouldn't have gone into engineering if you don't like math. But I'm not here to judge you. But if you don't like doing the math, you could just say, like, I'm just going to calculate the inverse tangent on my calculator. I'm going to keep 15 decimal places. I'm going to take the sine of that, and that'll work fine. Okay, but we can come up with a closed expression for a simplified thing. So here's a triangle that has an angle of the inverse tangent of mu. I'm just coming up with any right triangle that has this angle, inverse tangent of mu. So this is mu, and this is 1. So check that works out. You know, the tangent of this angle is mu over 1, and so if you take the inverse tangent, you get. I talked myself backwards. You know what I mean, though. Okay, so what's the sine? Well, to get the sine, we need to come up with an expression for the hypotenuse. So what's the hypotenuse of this triangle? Yeah, so we're just going to use Pythagorean theorem. 1 squared plus mu squared square root. And then what's the sine? Mu over this. So sine of the inverse tangent of mu is equal to mu over 1 plus mu squared square root. So the rho vector, it's not a vector, this rho value, that moment arm, is equal to r times this. And so the moment that's slowing this axle down is the weight times rho, which is weight r mu over the square root. That's mu. N? Those are both mu.
No, the one on the left.
Moment. Oh, okay. That's the... That's the moment that friction applies that slows down the rotation. And so another way to think of that is you would have to apply an equal and opposite moment to that externally somehow to keep this axle rotating with a constant angular velocity. Any questions about that? Okay, so let me do an example. Yes. Yeah. The way you're going to do problems is you're going to go through this derivation. So I'm not going to give you this formula. Yeah, but on the test I'm not.
Do we have to derive it every time we do the question, or can we
Yeah.
just memorize the end formula and then solve?
I suppose if you memorize it, there's nothing I can really do, but
Yeah, I didn't know if
I
it
would-
was going to be for points or something.
no, I would recommend that you just follow the steps, you know.
Actually, one quick question.
Yeah.
Why can we use the result of sine of tangent tan inverse of mu from the different triangle to get the result of the one that we were looking at previously?
Because we're just trying to figure out a relationship between angles. You'd see that any triangle you make that has any similar triangle to this, you know, that has an angle of tan inverse of mu, would give you the same value for the sine once you divided out the factors.
But wouldn't we have different values for each of the sides?
Yeah, but they would cancel when you got to since sine is opposite over hypotenuse, you'd have a multiplying factor on the opposite side and on the hypotenuse side. They'd cancel out and you'd get the same thing.
Okay.
You know, what if you had this triangle multiplied by 500? Then this would be 500 mu. This would be 500 times the square root of all this stuff. And the 500s would cancel, you get the same thing.
What I'm saying is, like, through the Pythagorean theorem, we derive square root of 1 plus mu squared.
Mhm.
Wouldn't those values by definition be different in another problem?
Okay, so think about a triangle that has 500 times the length. Okay. When you did the Pythagorean theorem to get the hypotenuse, you'd have this would be 500. So you'd have 500 squared plus 500 squared mu squared. You could just pull the 500 out, and you'd have a hypotenuse that's equal to 500 times this square root. And then when you took the sine, the 500 here would cancel the 500 here. So no, it wouldn't be different. Any similar triangle has those same sine and cosine relationships. Okay, so let's say we have a bearing. I'm going to draw it upside down, but then when I go into the problem, I'm going to do it exactly the same way. I'm just drawing it upside down to show that you don't have to really worry about that when you do these calculations. And let's say that there's an 8,000 Newton force pulling up on the bearing, 4,000 Newton forces on the two ends of the axle. The diameter of this axle is 0.06 meters, 6 centimeters. And let's say that the surface between the axle and the bearing has a coefficient of static friction of 0.05 and a coefficient of kinetic friction of 0.02. And we want to know what's the moment that must be applied externally to keep the axle rotating with a constant angular velocity. So I'm going to do a free body diagram of the axle in that side view. So there's an 8,000 Newton force acting down. There's an 8,000 Newton force acting up here. There's a normal force N. There's a perpendicular friction force. And you always, like if you look up friction coefficients in a table, there's always two values. Which one do we want to use, static or kinetic? Kinetic, because we're talking about something that's already moving and we're trying to maintain that motion. So this is 0.02 N. This angle is theta. This angle is theta. And what we're trying to get to eventually is this value rho. This R here is 0.06 meters. So theta is equal to, question?
The diameter was correct.
Oh yeah, you're right. Thank you. Yes. So this should be 0.03. So theta is equal to the inverse tangent of 0.02 n over n. So 0.02. And so rho is equal to the radius, 0.03, times the sine of the inverse tangent of 0.02. and you get a value for that of about 6.0 times 10 to the minus 4 meters. So it's a pretty small distance that that reaction force moves away from the center line.
Should this be in degrees or radians?
That is in it should be radians. Yeah, let me just make sure. It doesn't matter. It doesn't matter.
Yeah.
Because, if you calculated this angle in degrees, then you'd calculate the sine of that angle in degrees. Yeah, so either one is fine. And now finally, the moment is equal to that force of 8,000 times the moment arm of 6.0 times 10 to the minus 4. And you get a value of 4.8 Newton meters. So in order to keep this axle moving with a constant angular velocity, you have to apply, about 5 Newton meters to keep it going. Otherwise, friction is going to slow it down. Any questions about that? One thing to notice about all of these friction problems, these friction approaches assume dry friction. So these apply to like dry lubricants, graphite powder or whatever. But not joints that are saturated with oil. And the reason is that if you have a viscous liquid in the joint, the math of how friction is developed is different. It doesn't just depend on the normal force anymore. It depends on the speed of rotation. So you need a different approach if you're using oil.
Why wouldn't that just be factored into the coefficient of friction, though?
Well, yeah, because it changes based on the speed of rotation. So you could do it, I suppose, if you know what speed this is going. You could probably approximate in some way with, but that's something to be careful about with this. The math of this deals with dry friction. Okay, the other type of bearing, the second type, is thrust bearings. And I'm going to go through a derivation of the moment developed by friction when a hollow cylinder is rotated I'll call this force P. The angular velocity it's moving in this direction. If the inner radius is R inner, Ri, and the outer radius is Ro, what's the moment produced by friction? We're going to set this up as an integral derivation. So let's look at the surface of contact. It's a hollow circle where the radius of this one is R inner, the radius of this one is R outer. And the reason that we have to set this up as an integral definition is that if you think of thin rings of material, okay, every one of those thin rings has the normal force at this contact distributed the same way. So each one of these thin rings has the same amount of force applied to it, but each one of these rings is a different distance from the axis of rotation. And so even though the force is the same over, a ring like this, a ring like this, or the pressure is anyways, the force per area, they have different moment arms, and so they're producing different moments. So we're going to have to come up with an expression for the moment produced by some arbitrary thin ring, and then we're going to have to add those all up through integration. And so here are the steps to follow. So and we're going to use this as kind of our representative thin ring. So it's a circular ring with a constant radius. The thickness of this ring is d little r. The distance from the center of the axis of rotation to the thin ring is r. And what we're going to do is come up with an expression for the moment that's produced by this contact. Okay, so step one, we're going to first figure out the force per area. So the pressure is, you can think of it as the normal force divided by the total area. The normal force is P. The total area is just the area of a hollow circle, so that's pi times r outer squared minus r inner squared. And so every unit of area applies a force this big. And now we're going to use that pressure to find the infinitesimal amount of normal force spread out over that infinitesimal ring. Okay, so to figure out the total force over that infinitesimal ring, we're just going to take the pressure and multiply it by the area of that infinitesimal ring. So you can think of dN is equal to the pressure we just found times the area in that infinitesimal ring. And we can represent the area in that infinitesimal ring in terms of R. If we think of taking that ring and disconnecting two ends and stretching it out, that's like a trick with these kind of problems that you use over and over again. Then what you have is a thin rectangle with a thickness of dr and a length equal to the circumference. So you have P over pi times the quantity R outer squared minus R inner squared times 2 pi R dr. Any questions about that step? We're just taking the pressure we found and multiplying it by the area of one representative infinitesimal ring. And now that we have the normal force, remember it's not the normal force that applies the moment, it's the friction that depends on that normal force. So third, use that normal force to find the infinitesimal force of friction applied by that ring. D force of friction is just equal to the coefficient of friction times dN, which is, I'm going to rearrange some of this stuff. We got 2 pi times mu times p times RdR divided by pi times the quantity R outer squared minus R inner squared. Any questions about that? Okay, so that friction force now at every point is, at every place along this infinitesimal ring is tangent to that ring. And so to come up with the moment, the infinitesimal moment produced by that ring, you're just going to multiply that friction force times this distance r from the axis of rotation. So fourth, use this infinitesimal force of friction to find dm. Dm is just equal to R dff. And so now we have 2 pi mu p over pi times the quantity r outer squared minus r inner squared, all times r squared dr. And then the last step is just to integrate. Now we have the moment produced by an infinitesimal ring. We just have to integrate over all the infinitesimal rings. So the total moment is just equal to the integral from r inner to r outer of dm. So the moment is equal to, I'm going to pull all the constants out of the integral, 2 pi mu p. Oh, these pi's cancel. Let me get those out of there. So 2 mu p over the quantity r outer squared minus r inner squared times the integral from r inner to r outer of r squared dr. So 2 mu p over the quantity r outer squared minus r inner squared when you integrate this, you're going to get a coefficient of 1/3. So I'm going to pull that out too. And we have r cubed r outer cubed minus r inner cubed. And it sort of looks like there might be some simplifying you could do, but there isn't. Any questions about that? Okay, so let's say, as an example problem, you have a 10,000 Newton force pushing down on this axle. It's solid all the way through, it's not hollow, and that radius is 0.1 meters. The contact between the ground and the axle has a coefficient of static friction of 0.1, a coefficient of kinetic friction of 0.06, and we want to know what's the maximum couple we can apply before this starts to rotate. Okay, so what coefficient do we want to use for this problem? Yeah, this time we want to use static because it's at rest and we're trying to figure out when motion starts. So step one, the first thing we need to do is figure out the pressure. Bless you. So the pressure is equal to the total force of 10,000 divided by pi r squared I'm going to keep the pi in there because they're going to cancel out. So that's 1 times 10 to the 6 divided by pi. And now the next step is to figure out the infinitesimal force applied on a given, infinitesimal ring inside this thing. So to do that, we're going to multiply the pressure times the area. So our D normal force is equal to 1 times 10 to the 6 over pi times dA, the area of that infinitesimal ring. So that's 1 times 10 to the 6 over pi times 2 times pi times the radius dr. And now those pi's cancel.
Wouldn't that dr be over the entire thing? It seems you put the dr in the parentheses.
It doesn't matter.
Okay.
So you get 2 times 10 to the 5 dr for the infinitesimal normal force.
Would that be a lowercase r? Like 2 pi?
Yes. Yes, thank you. Yeah. Okay, so it's 2 times 10 to the 6 times r dr. And now we're going to use that to figure out the infinitesimal friction force applied by that ring. So dFF is equal to the coefficient times the infinitesimal normal force. So dFF is equal to the coefficient, that's 0.1, times 2 times 10 to the 6 times r dr, or 2 times 10 to the 5 r dr. And now the moment produced by that friction force, dm, is equal to r df. And so we get 2 times 10 to the 5 times r squared dr. And then the last step is to integrate this over the boundaries. So the total moment is the integral from the inner to the outer. This time the inner is 0. The outer is 0.1. of 2 times 10 to the 5 times r squared dr. So you get 2 times 10 to the 5 I'll pull the 3 out, and we have r cubed evaluated from 0 to 0.1. And that's 2 times 10 to the 5 divided by 3 times 0.1 to the third. And so the total moment is 66.7 Newton meters. So if you apply a moment to this axle bigger than 66.7 Newton meters, it'll start to rotate. Any questions about that? Anyone have a feel for, like, if you take an Allen wrench and really crank on it, like, about how much torque are you producing? Like, to put this in context? What?
Not Newton meters, but
Oh, yeah. So, yeah, in Newton meters, yeah, you're probably more used to pound inches or foot pounds or something.
I had to use a big torque wrench in the bottom of my car, about 60 Newton meters or so.
60, okay, yeah, right. So I'm more familiar with like bike stuff, so using like a little Allen wrench, about 10 Newton meters is pushing pretty hard on that. Yeah, if you get a big lever arm, you can get bigger, but 66.7 is a pretty big torque if you're applying it by hand.
Like pulling the bottom of the car.
Yeah, right.
Thing moved.
Yeah. Okay. There's only 10 minutes left. Anybody have any homework questions? That's all I wanted to say about this stuff. Any questions I can answer before we go? Yeah.
is the final in this room?
Yes. That's important. That could have a really big impact on your final score. Yes.
How many of the friction problem workers do you think are accurate?
Or what?
Accurate, like match the problems?
The solutions match the problems.
Yeah, how many of them?
My goal is 100%. It's probably less than that. I don't know what to say. I mean, if you don't like that, do the problems without looking at the solutions. You know?
Okay.
Any other questions?
On the final, how many like friction problems do you foresee?
Probably one friction problem, one internal loads problem, one other problem, something like that. Any other homework questions? Okay, well, thanks for taking my class. See you Thursday, or office hours.